with that, I shall start sharing my screen. Oh, I need to have screen sharing enabled.
Sure, I will give you. Wait a second. Yeah, here you go.
Okay, let's, and I shall share my desktop. Let's hope nothing untoward pops up while we're doing this. So hopefully you can all see the ChipFlow website, right? So this is a good place to go to start learning about what we're doing at ChipFlow and the product. But what you want to do if you want to try out the demos, go over here to where it says try the demo. And that'll take you through to a very pretty simple one-page documentation that you can walk through and get to the point of doing a tape out for a chip. Though I have to warn you at the moment, you're not going to be able, as a general participant, just going to this page, you won't get to tape out a chip just yet because we're limiting access to the tape out functionality. And this is mainly due to making sure that we've got something that's very stable before throwing open the doors to everyone. But you'll see at the end, you'll be able to, you can register for the beta, and then you'll be able to get a sign-up key, which will allow you to do that tape out. So talking you through this, one of the first things to do is get your system set up with the right tools for the job. We've got the instructions here that'll cover both Mac and an Ubuntu platform. If you're running another Linux, you're kind of on your own, but if you're running another Linux, you should be able to figure out roughly what the right thing is to do. And we're always happy to. This is an open Git on this, so we're always happy to take PRs if you want to start adding bits of instruction for your favorite platform. And the board we are using for this initial demo is the ULX3S, which is an open source FPGA board. This is what we use for testing that our code is running correctly before we turn it into a chip. So I've already done most of the setup on mine, but just to walk you through that, obviously you're going to need Python 3, you're going to need Git. I assume most people on this call will already have those in place. And then we use a Python tool called Poetry that allows us to have a really controlled release, so we can really guarantee that things are working when you try them out. So that'll be these two lines here. So if you're following along, feel free to start typing and copy these lines into your terminal and run them. So pipx, which is a nice little tool for installing more complex packages, and then Poetry, which is the tool used there. You may need to restart, and you may get a message that you need to set up an environment variable. You also need Docker, and we use this for building the software in a contained environment, the software that's going to run on the chip or on the board. And you'll also need a tool called OpenFPGA Loader, which is an open source tool for programming the ULX3S board, along with a host of other boards. So you follow through those instructions. If you hit any problems, do jump on our Gitter, which I think if you click here on support, you'll be able to see that there's a community Gitter, which you can go to. Let's open that in a new tab. So, and as you see, we literally just released this. So it's got three first posts.
Yeah,
so
Rob,
go in there and ask questions.
Yeah, Rob, there's a question from the chat, which is asking, is it can run on the Google Colab?
Ooh, it's a good question. So you'll be able to run most of it. The bit you won't be able to run is the programming the board, because that requires a local USB access. But apart from that, you should be able to run this demo on a Google Colab. And indeed, if you want to suggest some changes to some patches to the documentation to add that functionality, would be very welcome. So moving back, so there's the Gitter. Feel free to go and ask questions in there if you hit any problems at all. And then the first thing we're going to do is going to clone out the example system on chip project. So where your starting point is for any new designs, at least for now. So I pop up my terminal. Hopefully everyone can see that terminal. Is that there okay for everyone?
Yeah, I can see that. Perfect.
Yeah, cool. Okay, marvelous. Thank you, Simon. So we've cloned out the example socks repository, and we can just take a little look around in there. So the main things to look at here is my design. This has the Python, which is the design of a very simple system on a chip. It also includes a place to put your software that you're going to run on it. This is, again, a very kind of embedded board, though you can boot Linux on this design, I think. Well, no, there's a thing missing for you to boot Linux on this design, which is enough memory. But we will be adding support for one of the add-on boards you can get for the ULX3S, so you can test that out on the board. And Sim, which is the framework for simulating your design. The other kind of, and that's really main of it. There's a library directory here that's currently in this tree. It'll be eventually moving out, but this is a very early thing, and that's kind of all the infrastructure. And everything's driven through make here on this project. So first thing we're going to do is going to make init. So luckily I've already installed all my dependencies already. So I've already got everything ready there to go. I suppose the other thing to bear in mind in here is there's also a tests directory, which has a set of, allows you to do a simulation run and test the test functionality of your design. We won't go into that today, but we will expecting to do some future presentations around that. So to have a look, so let's get up the design and have a look at the code, right? So go to my design.py. So you see there's a usual set of imports at the top, things to be really worth talking through here. This is designed in Amaranth, which is a great project which allows you to use Python to design hardware. We're not writing, it's not kind of transpiling Python to hardware. You're using Python to describe the hardware, which we think is the right approach for this sort of these sort of projects. We have a couple of extra things which come from ChipFlow, which is the wrapper for the SOC and the kind of infrastructure for generating software and simulating the whole design. We're going to be using a VEX RISC-V core, so this will be a 32-bit RISC-V machine. And then we've got a set of components that we're going to pull into our design. And this is currently ChipFlow specific, but we'll be moving into the Amaranth project, hence the name. And so these are things like a GPIO peripheral. So for those who want Word, GPIO is general purpose input output. It's usually a set of wires that you can wiggle or listen to. We're going to use an SPI memory, which is a way of attaching a piece of memory, and it's one of the standard things on this board. So if you make if we made the chip, what we're plugging on, what we on our custom design would be attaching an SPI memory. We want UART. We want to be able to have a serial line so we can talk to it. And we want to have some RAM there, want an SRAM. We want a timer. Everyone needs a timer on any system for multiple reasons, mainly so it runs. And we're just also going to import a little bit of design which gives our system on a chip a unique identifier. So talk through, and then into the main chunk of the design. So one of the key things in this platform is it not only allows you to design your system on a chip, but also allows you to hook up the software that you're going to run on that system on a chip and generate the stubs and a little bit of a framework for you to start developing your little bit of embedded software. So we're going to set up, so this is kind of like our configuration of how the machine's going to look to the software that's running on it. So where's the RAM going to be? Where's our SPI devices going to live? Where's our GPIO going to be on the memory map? Where's our UART on the memory map? Where's our timer on the memory map? And where's our little specific hard-coded system on a chip ID in the memory map? We've got a few lines commented out. We'll come to those later. We're going to take this initial design and then add to it. And in Amaranth, one of the key ways this works is you have a method called elaborate. And elaborate for any component is really the bit which plugs together any underlying parts and generates any electronics to join those parts together. And this is where you do that piece of code. So first thing, when we're making a module, we are, so there's kind of like a whole load of initialization code, initialization hardware. So we're adding that into our module. I should point out, our module here is deriving from the ChipFlow system on a chip wrapper. So this is again providing all the infrastructure for a generic system on a chip. The next thing we want to be able to do is actually have a bus that we can connect all of our peripherals to. So here we are putting in an arbiter. This is the thing which allows multiple things to talk on a bus and arbitrates between them. And a decoder, this is the thing which, watches the bus and looks at the addresses and says, hey, you over there, this is your thing to handle, right? So these are quite important. And you see these are 30-bit wide. It's a 32-bit bus with 30 bits of address instruction, of address space on it. I think we are, granularity is 8 bytes, or is it 8 words? The next thing we want to add here really is the processor, right? So here we go. We're adding a VexRisk 5. We're adding a kind of a small version of it, the light version. And then we're adding the arbiter to that, right? So the arbiter connects to the processor. The next thing we want to do, add some ROM. So we've got some code that the processor is going to run. And here we are, we're actually going to pick out, we're going to have a flash ROM here. And it's attached on as QSPI. So this is set again, we're saying we've got some memory IO, and the thing that's there is our QSPI flash, which is, so we're selecting the one that's provided for the platforms. This is the abstracted platform under the hood. So that will allow us to both simulate on the FPGA board, and when we're on a chip, it'll be an infrastructure for connecting the flash. And then each of the components we add, we're gonna add them to the decoder, so the decoder can tell them, hey, your turn to listen to the bus. Next thing is a bit of RAM, definitely both ROM and RAM. This is quite kind of important on any design. And then a GPIO peripheral, right? Again, we're using the underlying platform to pick out the right GPIO peripheral, depending on the target that we're talking chips or to the or to the FPGA board. So just see a question on the chat from Indira. What kind of system on chips can you build? Are there any limitations architecturally or otherwise? So that's a really good question. There isn't any real limitations on the complexity of a design that you put together in this. The main limitation is going to be its speed under simulation. And then also, if you're using an FPGA board for, your development, the size that's going to fit on your FPGA board, and what IO you have on there. So initially, we're really much going to be quite embedded things that you'll be able to do easily. But in due course, we don't see any reason not to be able to do, billion gate designs, but that might be a few years off. In terms of foundry support, we have support for the Skywater 130 process. We have support for the Global Foundries 180 process, and we will be having support for another foundry, which I can't announce quite yet, but you'll keep an eye out. So hopefully, Indira, that answered your question. Moving on through, so we added an SRAM, we added a GPIO, we wanted a serial port, so we've added a serial port, and we're setting an initial baud rate there, 115,200. And then we are going to be adding timer. We've got a little unique identifier for the SoC, the system on a chip type here. And I think that's probably something cat related in hex, cat floof, I think. So if anyone knows gate cat, you'll know why it says that. And then we connect those up, right? We're connecting up the signals. We're making sure they're all these things we've added are now inside our design, so they're going to get elaborated. And we do a bit of connecting up of signals for the interrupt request. And we also want to be able to have a JTAG interface to the system on a chip. And then a little bit of special source here. So this is, if we're running a simulation, then we want to have a monitor to monitor what we're seeing on the bus, right? So that's going to help us to do any debugging. And then we want to be able to generate the software for our system on a chip. So we're saying, we're letting the software generator know where in ROM that code's going to live. So it generates the right addresses and where the RAM's going to live when we generate the software. And then we carry on adding, this is again telling our software generator, here are the peripherals that we're putting on our system on a chip. So telling about the SPI flash, the GPIO, the UART, platform timer, and the system on a chip ID. And we say generate some software. And that's it. That's our whole design. So this is going to generate us a system on a chip with a 32-bit RISC-V with some serial, with some GPIO, some RAM and some ROM. Let's have a look through. Let's walk through the sorry, excuse me. Walk through the rest of the process, and we can take a look. So first thing we're going to do is run it in simulation. So this is going to be really simulating how it's going to work if we made it into a chip. So first thing we do is make sim build. So this is going to basically create a binary. And the way that works actually is it takes the digital design, creates a C++ model of it, and then compiles that C++. Right? So it's actually quite a speedy way to run a simulation. So let's do that. Sim build. Give it a bit of time. You see it's building the various objects. And we've got now a simulator build. Of course, before we run this, we need to also make the software that's going to run on that simulated SoC, right? So let's make our software. So there we go, pretty straightforward. And we can dive into a bit what goes into that code if people want to. But now we got a ROM, we got our software to run on the board, we got we've got our system on a chip simulation. We've got the software to run on the simulation. Let's run it. Now this is, you see, it's kind of running quite slowly, but this is an entirely simulated 32-bit processor. So it's actually quite quick for a simulation perspective. And as you see, it's some of we can go look at the main.c that's being run. And it's these are the things that we're telling it to do. And we're done. It's initialized. And we can do Control-C to get out of that simulation. The next thing we can do is run this. And I'll just take you through the code a little bit. So again, so we go in My Design. We've got the software directory here. And we can read our main.c. This is the code that we're running on our simulated system on a chip. So here we go. This is the code you saw. So we're putting the strings in the sock type, our sock ID, our sock version, flash. We're entering, so QSPI is kind of quad SPI. It's a faster way of running that bus where we've connected, how we've connected the ROM, the flash. So this sets it up to run faster. And then we've got some commented out code, which again, we'll come to in the next stop. So let's carry on and run this on a board. So to run it on the board, what we want to do, make board build. And everything's so you've seen I haven't, in terms of the underlying componentry to do all these complicated bits and pieces, that's all wrapped up automatically, right? So you don't have, the only installed things you need to install those things we showed you at the start. This all comes from when you do make init. And as you can see, it's using the Yosis tool, which is kind of probably one of the game-changing bits of open source in this space, an open source tool to take hardware designs and turn them into a list of into a set of connected components. And here we go. It's written out our design. So now we can. First things first, we're going to load. So interestingly, we're going to load the software first before we run the design, because with this board, I can program the little flash, which is, I show you, is this little boy right there. So we can program the flash without having anything on the board programmed, and that's really helpful. So we're going to make board load software. That happen nice and quickly. And again, so that is using JTAG, which is kind of a very commonly used protocol across all system on chips to allow you to manipulate it. And so we're using JTAG to program our little bit of flash there. And the next thing we're going to do is then load on the design, and this isn't, again, this is not simulated, this is a design that's been converted into a form for programming onto an FPGA. So we can do make board load ULX3S, and that is going to then, if I hold this up, we should see it program the board. There we go. So that green light should mean we're good to go. Now this is connected over, so I've just got one single USB connection to this board, but which is used for all these operations, because it's a wonderful little design. And what it also does is provides me a USB connection, which is connected to the, a serial connection over the USB, and that serial is connected to the pins on there, which are going to be my serial pins. So let's get that up. So it's always a little tricky, this bit, because different boards and different machines will come up with different ways of naming that serial device. The way we do that is we basically, and this is only going to work on Linux and Mac, of course. Windows, we'll get to you guys if you're a Windows person. So we lsdev tty star, and we'll see there's a USB serial device here. So that's the one that's this board is providing for me. So we're going to connect to that. You're going to need a tool called Screen. If you haven't got that, you can install that using your package manager or with Brew on a Mac. You've probably already got it. And so what we're going to do is to this serial device that we found, I'm going to tell it how fast to talk to the board. And as you saw before, when we were writing our design, we chose an initial baud rate for the serial connection. So that's 115,200. So we're going to go screen to this serial here, 115,200. Right now, so if I press the power button here, that will reset this board, and then what will happen is the FPGAs now are designed, so that's what's going to run effectively, and that's going to then load in the program and execute it on that CPU that we created. So let's press reset, and yeah, we do. Now, as I mentioned at the start, there is one slight issue which I hit first time. So it's classic demo effect. Apparently, my board is slightly different than the one that my colleague used. And so it gets entering QSPI mode and then doesn't come out. So that's going to slightly impact my demo as I show you this board, but don't worry, it'll be fixed by tomorrow. If you want to hang on to that. And it's really, the reason is this little flash chip here. It's a slightly different model. So I'm going to come out of that. Now, screen's a slightly weird one. The way you come out of screen is you hold down Control, then you press A, and then you press backslash. That's the only sensible way to get out of this. So we're out of there. We've seen our board boot. Now we're going to go through a little bit of an example of adding a bit of, changing our design up a bit. Okay, so let's go and have a look again at our design file. And I remember there were some commented outlines. So these are going to form a little bit of a change for us. So what we're going to do is we are going to add, so we've got some LEDs there when we modified those. We're going to add a GPIO that listens to the buttons. So we're setting up that GPIO, and this is on this board is connected to some of those buttons there. So the first thing we do, we say where that's going to be in the memory map. And then we want to come down. And what we're going to do is we've got a new GPIO peripheral that's connected to those buttons. And you see that here we're using a bit of Amaranth called pins. And this is about literally which pins on your FPGA or on your chip when you make it, which pins are going to be connected to what, right? So we're saying, we're asking our underlying platform, let's allocate some pins for button GPIO. We know where they're connected on both our chip design and on our FPGA board and in our simulation, right? So that's why the platform is providing that. So we're getting those pins and we're adding a GPIO peripheral connected to those pins and adding it to the bus. And of course, we need to make sure that module is inside our design. And then we need to come down and make sure we're generating the software to talk to that peripheral. Okay. And that should be all the changes there for the hardware. Now we're going to change the software so we can actually see this work, right? So we go into our software directory and our main.c. And what we'll see here, we scroll down, is what we're going to do is just add in code that listens for those button presses and print something out on the screen when we see a button press. Okay, so this is just a really basic while loop. We're reading our GPIO register, which is connected to the buttons. You see we've kind of automatically been provided with a pointer that corresponds to the memory address that we set up in the design. And then we're going to read the buttons. And if one's pressed, we're going to say button one pressed. Two's pressed, we're going to say button two's pressed. I'm not entirely certain we entirely need that last line. It's fine. And then the other thing we're going to do is, so where we simulate this, we need to simulate our button presses, right? It's a simulation. So we need to go into our sim directory here. And we are going to open up the main.cp, which is the heart of the simulation we're doing of our design, right? Now, it's a little bit more complicated, this, but what we're going to do, so you can see, just to talk you through the simulation, we're loading the flash in on simulation, we're setting up a timer, loading the flash in, we've got a monitor, the wishbone, the bus, we've got a little timer, system timer that we're setting up there. And then let's simulate like somebody just pressing button one, then button two, button one, button two, button one, then button two. That's what we're going to simulate. Save us having too much compilation. So let's comment out these lines. So what we're doing here is we're ticking our system clock. And at various times, we're creating an index based off a system clock. So this is at at 100,000 ticks, press button 2, 150,000 ticks, press release button 1, sorry, 100,000 ticks, press button 1, 150,000 ticks, release button 1, 300,000 ticks, press button 2, and then 350,000 ticks, release button 2, right? And we're just going to loop around that. And these are basically the numbers that we saw before, which correspond with those two buttons that we saw in the software that's going to run on the design. Let's save that. Right, hopefully I haven't done anything wrong and we can just build the software. So first of all, let's make the software. So that's like building both the software to run on the board and the simulator. I think we also need to check that. We need to build the simulation. All there already, great. And I'm going to run the simulation. Lee, all right, booting, that's great, it's a good sign. Go without resetting mode, and hopefully. Oh, there we go. Button one got pressed. And then we go, button two got pressed. Ooh, did we not get button one released? Do you know what? Should we speed? Oh, no, we're not getting releases. It's going to be interesting. Should we see if we can speed this up? So let's go and have a look at our simulator. Let's make our buttons actually a little bit quicker in our simulation. So rather than doing it every 100,000, let's drop it down to 10 times faster. Yeah, well, I think our simulator is releasing and pressing button 2, but maybe our code isn't spotting it. We're going to have a look at our code. You see, we're only pressing out when it's pressed, aren't we? So what we can do, let's add a little bit of code to do that. So got these saved last buttons at the end here. So what we can do is do a bit of logic. If there was a flag set in next buttons, sorry, if a flag was set in last buttons, it's not set in next buttons, that means it got released. So that's what we want to calculate. So what we're going to do is we're going to invert. Well, let's see if I can remember how to do this. So we want to invert last buttons. And it with next buttons. Let's think. And we want to then also and that with our 1U. I'm coding my seat my pants here, so this could go horribly wrong, but let's have a see. Clarity. Also, if we only want to print this out if the previous one had the button pressed, right? So here we're only printing this if the button was not pressed before, say pressed. And this one we can say was it released? Give it a try. So the opposite way around. My brackets matching up? No, they're not. See if that works, eh? So make our software. Nope, I apparently can't type. What did I do wrong? 39. No, for some reason I did that. I did an extra A for some reason. Okay, that worked. Okay. Let's remake our simulator as well, because we sped it up, right? Let's run our simulator, see if it works. I could have broken this entirely. Who knows? Let's find out. Oh, I think I've broken it interestingly, haven't I? Well, what did I do wrong? Not certainly certain what I've done badly there. If I'm going to spot the error, let me know in the comments. Oh, well, we'll leave that for now. We're actually getting towards the end of things. So we're going to leave a bit of time for people to take comments. Unfortunately, like I said, there's a slight issue with the flash on my board, so I can't run this new version on here and show you buttons being pressed, which is very
Hi,
sad.
Rob. There is a comment actually by Karthik.
Yeah. The knot is missing at last buttons. Let's have a look. Where's the... well, you mean this one here? That shouldn't be a knot because we're saying if it was pressed before, we're only saying this if it was pressed before. Oh, hang on. Oh, that's why. This should be next. Yeah. I'm not quite sure. I've done something wrong. I've not thought this through properly. I was saying it's not if the last button was pressed and it's been released. Do you know what? Actually, we don't even need to do this, do we? So we can just say if that 0 if it's not there now and it was there before, then print it out, right? I'll actually use not. Try that. I'm sure there's something else broken. It kept saying button 1, press button 1, press button 1, press broken something somewhere. There we go! Yay! Got there. So for some reason it's not saying button. I'm just broken somewhere. It's still saying button 1 press twice. But yeah, let's have a look. Button 1 press, button 2 press, button 1 press. Broken. Oh, I know. There we go. That was that. See, spot the deliberate error. Right, let's do this again. We build and run it in a simulator. There we go. Cool. Well, we'll leave that running, I think, while I take some questions. So, guys, feel free to verbally ask it or ask over the chat, whichever you feel most comfortable with. And let's take that last 10 minutes just to take questions.
Yeah, thanks, Rob. And yeah, it's nice to see it's running. And if anyone have questions, you can unmute yourself, or you can post your question in the chats. I can read out. Yep.
Oh, we didn't actually run. Actually, sorry, did forget to do the one last thing, which is how do we actually make a design? How do we make a chip for manufacture, right? So first of all, we're going to make this intermediate file, and then you run Silicon Prepare. Now, unfortunately, for at the moment, you're going to have to sign up to the beta before this will work. But there's one I made earlier. So go down to the load up Hey Layout, which is a really great little tool for viewing what. So when you're making a chip for manufacture, the thing you send to for manufacturing basically is something called a GDS, or you can call it artwork. And this is a file format. It's basically a whole load of layers of pictures which say what the layers are going to be when you make the chip. So if I go to my folder, Okay. Right. Code, ChipFlow. We were doing this in demo. This new isoc.gds. And here you go. This is something suitable for sending to manufacture. And I think probably maybe show and hide a few layers here. Remember how to do this. Yeah, it's working. So we just zoom in. Zoom in. I'm not very good at using this. But yeah, I think I'll leave that at this point because we obviously won't have much time for pictures, for conversations. But you can zoom in on that. You'll be able to see the transistors, the wires, how it was all connected. And there's some great courses from Matt Venn to check out that will help you understand GDS and visualize it and use K-layout. So yeah, there we go. Thank you very much, everyone. So yeah, questions.
We have a question.
Who are your typical customers? Thank you. Yeah, seen it. So who are your typical customers? Do you also have a services model? Really good question. So we're still, I mean, I was like, it's going to be probably halfway through next year by the time we're available for a full beta and being able to take on typical customers. But early days, we expect to see automotive being an area of interest, personal devices, healthcare devices, and there's some other areas which are coming along which I can't quite talk about just yet. But we'll be able to see a bit of news about that in the new year. Do you do some timing analysis before downloading or during simulations? Good question. So we do timing analysis of the place and routed design, and you get that back. I think there's some interesting questions we're in the process of answering about how to really hook that back to your design in a meaningful way. I think there's a little bit of figuring out there. But yeah, and again, you can get that timing information out in simulations. It's not in this demo. Did that answer your question? And yeah, and the layout is entirely automated. So we're working with a project from the Sorbonne in Paris called Coriolis, which is a place and route tool. Also supports analog and mixed signal. And yeah, we automate that going from the design. One of the great things about using these open source components to pull this capability together is we really can flow through the information from the high level information of the design all the way through to place and route. Now, we're not going to be like the massively competitive power performance and area, not at this stage. But really the aim here is to have something that's simple and works. So Indira, did I answer your question entirely? Sutansu, did I answer your question?
Yes, thank you. I just had a quick follow-up. I'm sorry, I think you just mentioned about the quality of results, but I was wondering how who are this whole software-driven model to get to a prototype really quickly and be able to work with that, make design changes, and see how it will potentially behave in hardware. How can a typical RTL designer use this, right? I mean, do you see a barrier to usage from Python and so on? I'm kind of interested in your vision on that.
Yeah, it's a really interesting question because, I mean, well, obviously what we're trying to do here is enable a lot more people to be able to do hardware design. We almost, we almost don't see, traditional RTL designers who are kind of already have their ways of working and are comfortable in the commercial tool sets, right? We don't see them as targets, though what we think is going to be the case is over time is going to become, this is just going to be a better way to work. So yeah, we will, the aim is to get to, competitive quality results, especially on power and performance. We're actually not as concerned on area, because what we want to be able to support here is companies being able to manufacture at the volumes that they need, right? And if you're manufacturing like 100,000 chips or 1 million chips, your design costs form 70 to 80% of your die cost, right? Your NRE amortized over your run, it ends up being certainly way over 50%. So area initially for us, we're not so concerned on. The focus is really going to be on power and performance in the quality of results. And yeah, but yeah, so one of the things we've got in here is the simulation backend here allows you to not only do it in Python, you can also pull in any other hardware design methodology in there. You can pull in Verilog and VHDL. And it allows you to be able to pull out a signal over any of these components that you pull together. You can inspect that signal and see what's going on there. And gradually we're going to be able to actually hook up like higher level monitoring of component of bus signals and signals in the design, and really help you get a better understanding of the design. And so some of that's actually going to end up being better than the commercial tools.
Okay, thanks. Can I just have a very quick follow-up? I mean, do you see a path into like a virtual prototyping type of solution, a path into hardware emulation and so on? Because it seems like a great way to bring all that up front in the design cycle, right? So
yeah, absolutely. I mean, I look forward to a day when you can fire up AutoCAD or one of the open source CAD tools, make a design, fire it, programmatically generate your PCB, programmatically generate your CPU, and get it all manufactured and built, right? That's definitely where I want to see this all go in the end.
Thank you so much.
Yeah, you're welcome. Thank you. Great questions. Sudhanshu, great to enter. Yeah, absolutely. Yeah, I am quite often down in Cambridge. I actually live in the Peak District. The entire ChipFlow team we're geographically spread. We started this in lockdown, so we're remote by default, which means as we do grow, we will be hiring across the world, just get the best people wherever they are, and really help bring up this whole ecosystem. So yeah, it'd be great to meet you there.
So hi Rob, I have a question.
Okay, so brilliant. Go for it.
What are the main features of the beta version, and what are the criteria of being selected? Like you select a first come first serve, or any specific application depends or something like that?
Yeah, that's a really good question. So really what we're basing the initial designs off what capabilities we're most comfortable with, but also being guided by what we're seeing in terms of we're going to be we're opening up the alpha now. We're going to be looking at who's signing up for the alpha, and that's going to help us guide us on what we're going to be bringing out as the initial designs that are market relevant for the areas we're seeing the most interest.
Okay.
My call. Did that answer your question, Simon?
Yeah, thanks.
Thank you.
I think we can go for one more question. Yeah, anyone have a question, please share it on the chats, or you can unmute yourself and ask. Free to ask with Rob here. Yeah. So I think just let's say follow up. Initially, I think yeah, I think someone asked regarding the Google collab, right? So it's I think the issues you mentioned about like a serial, right? Or the USB access.
Yes, yeah.
And I think like we have Travis mentioned about web serial. So
yeah, it's an interesting thing to try out. The web USB would be the way to do it. Yeah, if anyone's interested in getting involved in supporting that, that'd be, you know, there's all sorts of space for collaboration and to get on and start helping building out this whole ecosystem. All that part of the system is all open source, so do come on and feel free to join in.
yeah, that's a beauty of open source. Yeah, Travis, would you like to add anything on this one, web serial? I think in the work will be like very less, like if you use collab, just go there and do some templates, and we don't need to install any software or something like that. Yeah, that will be.
Yeah, it'd be really cool. I'd love to see that. Yeah, Google Collab or Gitpod. You know, these are all great things that I'd love to be able to just have a really, like, you know, I think my desire is like someone sitting on a laptop in a coffee shop somewhere can design a chip and get it made, right? And the simpler we make it and simpler we get started, the better it is.
Yeah, cool. So I think that's all about questions. And thank you, Rob. Thank you for time, and thank you for.
Thank you. It's been really enjoyable. Well, I look forward to doing this again. You know, when we maybe have the next alpha out and a bit more to show as well. Thank you, Indira.
And I also shared the Academy Discord channel here.
I'll join the Discord, and again, feel free to join our Gitter if you have any questions or just want to ask anything comes up. Yeah,
sure. And we actually run weekly IC design study group. It's led by Jason. And
amazing.
Yeah. So yeah, feel to join there and ask your question. Rob will also join there. So you can expect a good quality answers from there.
Yeah.
And we also have, like tomorrow, we also have another session that's actually cellular IoT. So
wow, very cool.
Yeah, you can join there also. It will be if you go to the event list, you can see.
Yep. Amazing. You get to see how old I am now. Cool. Thank you very much, everyone. I look forward to meeting you on the Discord or on the Gitter, and yeah, I'm sure I'll be back with more.